And we're back for the half-life part. So what is a half-life? Half-life is the time it takes for half of an element to radioactive decay. So here's carbon-14, which relates to carbon-14 dating, which is important. So if you have 10 grams of carbon-14 in 5,730 years, half, statistically, is going to decay. So if you start off with 10 grams, in 5,730 years, you'll have 5. So knowing how much you started with and how much you ended with, you can see where on this curve you are. And based on this curve, you can tell what age it is. So hence carbon dating. Carbon dating. Tell me where half you've been all my life. Get it? Half life? Huh? 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 I know. Okay, so here's carbon-14. So carbon-14 has a half-life of 5,730 years. It's continuously forming the atmosphere. What happens is cosmic radiation, here's a cosmic radiation coming in, hits the nitrogen, turns it into carbon-14. Carbon-14 is radioactive, and that is absorbed by the plants. They take the carbon dioxide, turn that into food, plant. We eat the plants like the bananas, yum, 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 yum. And that carbon goes into us, and as we continuously eat, we continually refresh our carbon-14 levels. But once we stop eating, or we die and stop eating, then we stop getting the carbon-14. So the carbon-14 stops coming in and then starts that decay curve, and we can date something based on its carbon-14. Now, of course, there's a dinosaur here. We'll see why dinosaurs aren't carbon-14 dated, but you'll see why in a second. So here, if we look, I'll move this out of the way. So here, if we look over here, carbon-14 dating, that's organic things with carbon in it. So that can be, I can't see the bottom of the slide. There you go. That you can go up to 100,000 years. So that's good, but not good for dinosaurs. So for many of the things that, how old is it? I don't know. Let's do carbon dating. Let's find out how old it is. Some things that don't have carbon in it, you could use things like coral or fossils or clay or even rocks. You can use uranium lead dating, which go back, wow, look at that, 4.6 billion years. And coral and clay, potassium argon dating. So there's a lot of isotopes you could use for dating. So what they do is they use these different isotopes to date things like rocks. Now you can't do the bone because obviously that's not 65 million years, but you can date rocks, and not just rocks from Earth, but rocks from the moon and rocks from space like meteorites. And if we do these datings, we find out that most of these rocks are for about 4.5 billion years old. That's as oldest as we can find it. So that's very interesting that you can't find anything older than 4.5 billion years. Very interesting. So is the universe 4.5 billion years old? No, not really, because you have to have the uranium to start. So how'd you get uranium? Well, we'll find out in a minute. So here's some other isotopes for dating. We got the carbon-14, we got potassium-40, we got rubidium, we got uranium-238, you got radium-235, millions to billions of years. So we can date things that are very old or not so old. And what else can we use the nifty radiation for? Well, a lot of those isotopes, which you'll see more isotopes in a minute, not only good for dating, but also good for medical purposes like x-rays, PET scans, and technetium for a stress test. So if you have a heart condition and you want to get a nuclear stress test for your heart, they'll give you some technetium. Yum, yum, yum. And then you'll glow in the dark. Now, of course, here's the irony behind radiation is that we mentioned earlier that ionizing radiation can cause cancer. But here's the interesting thing, that it can also be used to treat cancer. That's very interesting. Isn't science interesting? So you could use radiation therapy. You can use the cyber knife, which is a new way of doing it. Or you could do things called iodine for if you have a thyroid problem and you're supposed to thyroid, you take radioactive iodine, which is iodine 131, which goes to your thyroid and will radioactively decay in your thyroid and will kill the thyroid cancer cells. And of course, they also have cobalt and these little seeds. So if you have prostate cancer, they can insert one of these little seeds into your prostate, which will radioactively kill the prostate cancer without having to go through surgery. Isn't technology great? Okay, so here's a whole bunch of different types of isotopes. We got technetium, which I mentioned earlier, iodine 131, we talked about that, iridium, fluorine, iodine, cobalt, cesium, americium. Here's americium. Here's gold. Wait a minute, gold? I can make gold radioactive? Yes, you can, but there's one problem. Look at the half-life, 2.7 days. Doesn't last long. So you really can't use gold. I can't make gold like the alchemists wanted to. Not very profitable. And of course, zinc and manganese. So lots of fun isotopes to do. Now comes the fun part. Fission and fusion. Fission is elements when they break into smaller pieces. And not radioactive decay, but actually splitting, not in half, but close. So if you can control it, guess what? Nuclear power plant. If you can't control it, boom, nuclear bomb. So to remind ourselves about nuclear fusion, so we take uranium-235, they hit it with slow neutrons in nuclear bombs or nuclear power plants. It turns into uranium-236, which is unstable, and that splits into krypton and barium and 3 neutrons, which can go off and do the same to their friends, and so on and so on. And then if it gets wild and crazy, it goes viral / nuclear. But hopefully we don't do that. But notice this energy. Now, we're going to talk later about energy of bonds, but this is nucleus energy inside the nucleus, which is a lot of energy. And how much energy is that? Let's see. Well, let's do a little math. Einstein came up with this great equation, E equals mc squared, and E is the energy, M is the mass, and you're not losing a lot of mass. It's a tiny, 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 tiny part of mass, times the speed of light squared. The speed of light is this huge number, 3 with 8 zeros. You square that, it's 3 with 16 zeros. And you multiply that big number with the tiny, tiny, tiny mass, and you get a decent amount of energy. And if you have a lot of those, you have a lot of energy. And what can you do with that energy? Well, you can make a bomb, or you can do something really cool, or should I say really warm. And what they do in nuclear power plants, this is kind of like a view of the inside, is that it heats up water. So making coffee with nuclear power, I guess you could if you really wanted to, but what happens is it makes a steam. The steam runs a turbine. The turbine runs a generator. The generator generates electricity, and that goes into the power lines, and then goes to your house and turns the lights on. So where does power come from? Well, it comes from a generator somewhere. And where does the generator get its power from? From rotating somehow. What's it going to do? Boiling water is most frequently used. So here we have nuclear power generating that boiling water to run the turbine. You could also use, in a dam, it's just the gravity pushing the pressure of the water. So that runs the turbine, which is hydro electric energy. But of course, you could also have other things that turn turbines. Like you can have a whole bunch of little mice going, little hamster wheels, and they could generate electricity too, but not on a scale that we need. So hence the nuclear power plant. Now, of course, you can burn other things like coal and oil and gas, but we'll get to that in a minute. And actually, in a minute is right now. Where does the U.S. get its energy from? Well, in 2014, we got 39% from coal, 27% from natural gas, 19% from nuclear, some little hydro, 6%, wind, 4%, biomass, which is just burning wood and stuff, 2%, some liquids, a little bit of solar, other gases, geothermal. We don't have much geothermal here in the United States, a little bit, but more up in Iceland. They have lots of geothermal up there because lots of volcano action. So let's talk about the US and how we've been using fuel and making energy for the last, since the beginning of the country, since 1776. Look at that. Way back then, that's all we did. We burnt wood. That's it. Burning wood, burning wood, burning wood. Now all of a sudden, we're starting to get some industrial revolution stuff going on there. Let's take a look. Let's see. We're burning more wood. Population's increasing, not just for heating. We use it for heating. We use it for cooking. We use it for fires, keeping the animals away. And then all of a sudden, someone says, hey, instead of burning wood, let's burn this stuff called coal. Ooh, look at that. All of a sudden, shoots up. Oh my goodness. Now coal use goes way up. And of course, obviously people still burn wood, but guess what? Coal goes up. And then after that, guess what else? We discovered oil. We could use oil and burn oil. And then we can make cars. And then cars burn gasoline, which is oil. And goes up. Wow, look at all that oil being used. And look what else comes up afterwards. Ooh, this leftover gas that was coming out of the ground, which we now know is a little bit of helium, but also gas. Hey, we can burn that too. Oh, goodness gracious. And all of a sudden we start burning that gas and we collect it. And now it's getting very popular to get the gas out. Notice what's happening to coal. Coal's going downhill. All these other guys are going uphill. Very interesting. Trends. Let's look at these trends. Coal. Over the last 20 years, downhill. Coal, down. Natural gas has been going up. We've been fracking and getting more natural gas. And of course, oil. Our oil use has gone up too because more people have cars, more people burn gas. But look at this one. Solar. Boom. So that shall be our future because the sun doesn't run out. Thank goodness. Well, at night it runs out, but not for another couple of million years. So that is super. That is where the future is. The green future. Where does NJ, New Jersey, get its energy from? Let's see. We got nuclears here, 50%. Here we got natural gas, 42%. Very popular now. We got renewables, which is nice, 6%, and only a teeny tiny bit of coal, which is good. But take a look at this. Why is the natural gas higher? Well, natural gas is cheaper. That's why. So now we're using more natural gas. And nuclear is going down. It would be nice to have nuclear, but the problem is nuclear waste, which is another story of another day. And here's a whole bunch of facts, which I will save for the next slide.